Great.
Okay. You see I put it in slideshow mode.
Yeah, we're still in the correct mode. Thank you, Simone.
Okay.
And floor is yours.
Thank you. Thank you, Flago. So yeah, today, so I'm going to present the developments we did together with ESI and the vendor AMD and NVIDIA in the porting of OpenFOAM to GPUs, which is an important topic that is required a lot of efforts and discussions. So it's a very short presentation, but we will see, let's say, the main issue we encountered and how we try to solve it, and some results, say, using a very simple benchmark. So let's start with the current approach is implemented in OpenFOAM OpenCFT version. Okay, so up to now, the only porting to GPU available as a submodule in the repository of OpenFOAM OpenCFT is a hybrid approach, where only the linear algebra part of the OpenFOAM workflow is offloaded to GPUs. Okay, and this is accomplished by using two libraries. One is Patsy4Foam, which works as an interface, as a middle layer between OpenFOAM and say Patsy, or say in general Patsy and other third-party libraries. And Foam2CSR, which is a utility used by Patsy4Foam to convert the metrics from say native OpenFOAM format. I call it in some papers and deliverable LDU order at CO, means that the matrix is splitting into three matrices: lower, diagonal, and upper. And for lower and upper, we use the coordinate format in ordered fashion. This approach, as I told you, only offloads the linear algebra part to GPUs. So according to the Amdahl law, the speed up you can achieve is strongly related to the time spent in the linear algebra part of the entire workflow. So if you have an incompressible problem, for example, where the threshold solver requires many iterations to converge, this approach can give you reasonable, let's say, improvement. But if it is not the case, so it converges very fast in few iterations, the overhead of conversion and offloading the metrics to GPUs in some way overcome the advantage of solving on the GPUs. So from my experience, this speed up that can be achieved by using this approach is for the hardware I tested, which are NVIDIA Volta and NVIDIA Ampere, is no more than 3 pairs of speed up. This number can be in some way double if we are going to use Grasshopper, since from the test I made there is a sort of 2 pair of advantage, 2 pair of speed up with respect to Volt Ampere. So what about try to push in not only the linear algebra part, but also the discretization of the operators in order to, let's say, have metrics and a solution on the same hardware, without, let's say, making this, let's say, back and forth between CPU and GPUs. So together with AMD, we deliver a solution which is is not still in repo official of OpenFOAM. We try to push the entire workflow of OpenFOAM, so assembly and solution, on using two main aspects: OpenMP for target offloading and unified memory. Unified memory physical is available on the recent AMD GPUs, which is, let's say, call it APU, with accelerated processing unit, particularly the last version, which is MI300A GPU, which presents, as you see in the picture, a unified memory between CPU and GPU. So so there is no need anymore, let's say, to move data between host and device because the memory is completely shared. Using this approach, we have some advantages. One of the most important one is that it can be, let's say, put a few lines into the source code, mainly pragma directives, where you have the most expensive loops. And because the data management is completely done in an implicit way by the driver, also by the card, since the memory is completely shared between CPU and GPU. Also, in order to, let's say, to reduce the overhead of allocation and deallocation that normally OpenFOAM uses a lot into the workflow, we introduced a memory pool based on the Umpire library, which give you a reasonable speed up in try to reduce the let's say, overhead of allocation and deallocation. But for sure, the big advantage is the fact that there is no anymore within this recent cards distinction between host and device memory spaces, which is an important point. But there are also limitations to this OpenMP approach. And I reported mainly three cons. The first one is that not all the compilers compiles the code successfully. For the moment, for example, the VIA compiler does not work, and we only tested using basically CLang, in particular the CLang delivered with ROCm, which is a software delivered by AMD. The problem is that the other not good aspect is that the performances on discrete GPUs are not good. We basically made some tests using this approach on Hopper, Ampere, and MI210, and we see that 60%, or probably more than 60% of the time, is spent in page migrations. So if you don't have a machine that in some way has fast connection between, like in Grasshopper, between host and device, or a completely unified memory, like in MI300A, performances are very bad. And in the current supercomputers, there is no Grasshopper and MI300A valid at the moment. The other aspect is that if you want to use a single source code, so basically adding pragma directives, it means that you have to live with the fact that you need a lot of atomics, because OpenFOAM uses a lot of the owner and neighbor vectors that in some way implies the use of atomics. And if you don't have a good implementation on hardware of atomics, the performances are very bad, like the case using the MND MI200 or 210. So in the project, we delivered this solution, which is probably promising in the next say coming supercomputer, Grasshopper and MI200A. We try to work on a different approach, which is called ZofOAM, which is a library we deliver and we are still working on, which basically refactors two core libraries, it's the libraries of OpenFOAM, which are OpenFOAM and finite volume. So the idea is to develop a plugin that, let's say, rely on OpenFOAM and try to introduce some, let's say, design pattern that can be useful to run on GPU. But different to the previous approach, we have an explicit data management, okay, using a memory pool we implemented natively. So we tried in this two libraries we refactor using the visitor pattern to separate the data structure that we have in OpenFOAM and the algorithm that acts on it. if you use this approach, you have basically several executors, one executor for each hardware, and this executor acts on the data structure of OpenFOAM and performs operations between fields, which are used everywhere in OpenFOAM, using so for example, the libraries of the vendor libraries or kernels developed by yourself, like CUDA kernels or heap kernels and so on. For MPI, there is no change. So we still use pstream and combined with CUDA MPI aware. And regarding the linear algebra, we, let's say, decide to offload, not offload, but to say push the metrics to external libraries like NGX in order to, let's say, try to use a multi-grid implementation provided by vendor. So we only natively implemented simple solver like conjugate gradient and biconjugate gradient. So at the end of the day, we delivered a code which looks very similar to the OpenFOAM one. So we used a sort of domain-specific engine equal to the previous. Okay, you see from this picture that basically icofoam looks like the same, except that we have now a different name for the volume field for the matrix. We put basically the prefix device before. And we use different namespace where we add our operators discretization using the visitor pattern, so using our, say, device executors. The issue of this approach is at the moment we have several classes duplicated, and we hope that in the coming months to, let's say, work with ESI and try, let's say, to push some stuff into the SI OpenFOAM version in order to reduce the code we deliver in ZofOAM. So let's try to present in the last 10 minutes some results we obtained using ZofOAM. And for the moment, we only deliver results using the laminar 3D delivering cavity, but we can see this test as an upper bound of performances you can achieve with this approach. I think that in a, say, less or run simulations, the results will be lower than this, but you can have an upper bound of performances that you can, say, use as a reference. For example, we run on a 1 GPU node of Leonardo, or the current supercomputer we have here in CINECA, and we perform saturation test by running the delivering cavity from the case S with 1 million cells to the XL case with 64 million cells. And you see that you have a huge speed up, a huge amount of speed up moving from the case S 1 million to the case M. So the speed up moved basically from 2 pair respect to 1 CPU node to 20 pair respect to 1 CPU node, and try to, let's say, to push to arrive at a sort of plateau from 27 million and so on. So, and we have, so the best number we achieve is around 26 pair of speed up, 1 GPU node versus 1 CPU node. The comparison is done using fixed number of iterations. Okay, we increase the number of iteration because we are using Jacobi as a preconditioner, and if you don't increase the number of iteration, the solver does not converge, because Jacobi is not good preconditioning for the pressure solver, but is not the simple precondition we implemented so far. And so the comparison is done using the same solver between CPU and GPU. In these slides, I also reported the performances that you have using 32 CPU Ice Lake that we have on Leonardo compared to 1 GPU, 2 GPU, and 4 GPU. Okay, in order to see, so the speed up, the scalability between 1 and 4 GPUs, and also the speed up you have between 1 CPU and 1 GPU node. And you see now that the maximum we achieve is 26 pair with respect to 1 CPU node. So we try also to modify the solver, the pressure solver in particular, for the S and the M case, moving from the simple Jacobi as a precondition for the conjugate gradient using a multigrid provided by NGX, combined with the same solver, a conjugate gradient. And you see that you have a speed up, okay, is 1.4 per for the S case and 2.8 for the M case. This speed up is using the same number of iterations, but one can argue that using multigrid, the number of iteration should be much more less, yes, but you still have a speed up using the same number of iterations. So you can see that you can have an advantage using multigrid and fixing the tolerance with respect to fixing the number of iterations. So the speed up using NGX is still higher with respect to simple Jacobi. And also here is another plot that we obtained a few days ago by comparison the hardware between the Ampere that we have on Leonardo, which is also codenamed Da Vinci, which is a little bit different from the standard Ampere GPU that you found on the market, Hopper and Grace Hopper. This is a hardware comparison using the same solver, the same number of iterations, same benchmark. And you see that basically there is a sort of two pair of speed up between Ampere and Grace Hopper. So if one has, let's say, one GPU node with 4 Grace Hopper with respect to 32 core of Rice Lake using the same solver, we can say that the speed up is 26 multiplied by 2, so sort of more than 50 pair. This is now the. I know that this is a sort of upper bound, as I told you before. We now are working in, let's say, putting on using our structure also turbulence model on GPUs, and we hope in the coming weeks to run some, let's say, less simulations in order to see how much far away we are from this, let's say, reference number using Leonardo and also Grace Hopper. I finished my presentation. We have 4 minutes for